Okay, so why we were discussing interpolation? Because many times we would like to do geometric transformation of images. For example, we may want to rotate an image, or we may want to align two images, which is basically called registration of two images. Or sometimes there are lens distortion in images due to so there is something called lens distortion because of the spherical nature of the lenses in the thing. So you may not get a perfect image. So there is something called dewarping. Anyhow, that so these are different applications where there is images need to be geometrically transformed. So basically, geometric transform is we would like to change the pixel coordinates. So the spatial location of the pixels are going to change uh, depending on, so xy so let us say vw is your pixel coordinate in the original image, and xy is the corresponding pixel coordinate in the transformed image. So there has to be some transformation function which will change v comma w to x comma y. So for example, if you are just shrinking the image by a factor of 2, the transformation function is simply v by 2 and w by 2. And but do remember that mostly we will be interested in t inverse. So once we know the t, we'll have to apply t inverse to get the original intensity values. So normally what we do, we represent t as a matrix, and we actually go for homogeneous coordinate system. So have you heard about this homogeneous coordinate? So who so if you would have studied computer graphics, you would have studied about it a lot, because almost all the computer graphics operations are done in homogeneous coordinate system. If you have studied the 3D geometry, you would have studied homogeneous coordinate system. But if you have not studied, I'm not going to go into detail, but just the idea uh, is basically a mathematical trick by which we try to ease out our implementation of geometric transformations. So what we do, we append. So if xy is our coordinate, if xy is our 2D coordinate, we'll append one more coordinate with 1. If we have 3D xyz, we'll again append 1, so we'll get into 4 coordinates. So last one will be 1 here, and I'll so this t I'm representing it by this kind of a matrix. This particular matrix is called affine transformation matrix. I have written here. So whenever we want to do affine transformation is basically simple transformation like translation, rotation, scaling, and shear also. So it's so these all those types of transformation can be represented in this way. So the last one, the last column will be 0, 0, 1, and you will have some value, some values here. Will show what these values are here for different operations. So if our matrix, if our transformation matrix takes this type, we know this is an affine transformation. And sometimes you will have to do perspective projections. So remember, you know, pinhole camera model, it's a perspective projection. So in order to get we divide by the depth of the distance and the focal length. So that is kind of a non-linear operation, because there is a division involved here. But whatever whether it is a non-linear operation or it is a simple affine transformation, all these operations can be implemented in a single framework using homogeneous coordinate system. So that is the advantage of using homogeneous coordinate system. It allows us to represent all these various geometric transformation in a single framework, and we can implement all of them simply by simple matrices. And if you want to do multiple transformation, let us say you want to first scale up and then rotate and then translate, you can just you can just concatenate the transformation represented by each type of operation and multiply them, and you will get the resultant transformation matrix, which will represent the combined operation that you want to do on the image. So I'll show that in later. And then once you do the transformation application, So once you get the transformation matrix and you apply it to your original image, then you will get a resultant values, and from that if you have to get back your x and y. So sometimes what may happen, your resultant matrix may not have 1 at the end. It will have some non-zero it may have some values which is not equal to 1. So in order to get back our matrix, our actual coordinate, will divide it by the last values here, because we need one here. We have actually appended one here. So ideally, whatever value we should get, we should get one here. But if it is not one, we divide it by w so that this becomes one. So our new x, our x dash, that is the resultant coordinate in the new image, transformed image, will be this. So these are standard transformation matrix. So this is an identity matrix. Basically, if you multiply it with this, there will be no change in the transformation. If you want to scale up in x direction or y direction, then the transformation matrix that you can choose will take this form. So depending on if you want if you want to scale up in x direction, you have to put that scaling factor here, and the scaling factor in y you have to put it here, and then multiply this with our v, w, and 1. Here we have to do the actual matrix multiplication, and you will get the resultant x, y. Similarly, if you want to rotate it, depending on the theta value, how much you want to rotate, you can substitute this transformation matrix, and you will get the new transformed things. If you want to translate it, then the translation factor should be, so if you want to translate the or entire image or only sub part of the image, then how much degree you want to translate in x direction, y direction, you can put it here. And similarly, this is for shear factor, where if you want to stretch it in vertical direction or horizontal direction, then you can put that factor here. So you can see all these matrices, all these transformations are called affine transformation. The last column will always be 0, 0, 1. And you can concatenate them. As I said, if you want to do multiple operations in one go, you want to rotate as well as translate as well as shear, then you can basically multiply all of them. You can take a transformation matrix, then multiply with the rotation matrix, and so on. So you can take the transformation matrix, multiply with the, let us say, scaling matrix, multiply with translation matrix, and so on, and that will give you the resultant combined transformation matrix that you want to do it. Any question in this? I'm not going to ask much. It is just background information that it was needed, so that's why I'm covering it. It's not so much. So this is a simple exercise. If, for example, if you want to scale the image by a factor of 1.5, what will be the T matrix? If you want to translate it to the right by 10 pixels, you can just put the values in this matrix and you'll get the corresponding image, corresponding transformation matrix. And if you want to do all the above three, just take this matrix, and this, and multiply them in that order. You will get the resultant matrix. So why I'm discussing this? Because one of the important pre-processing step that may be needed is called image registration. As I said, we will many times, either we want to take a difference or whatever, many times we will have to align two images so that the corresponding locations, they map to the same locations. For example, in this, these are two aerial images taken probably at a different time instant or from different camera itself, because this one is a different type of modality, this is a different type of modality. So they are not perfectly aligned. As you can see, this lake portion, the spatial locations are somewhere here, while here the lake is shifted in this direction and so on. It's not perfectly aligned here. And let us say if you want to find out what changes happened And then we'll have to take image difference, and to do that we'll have to either rotate one of the transform on the image to align it to the other one, and so on. So here if we are trying to align this image to this image, then the transformed image will look something like this. So how you do this? If you have to do this, how will you how this image registration is done? Hmm? Correct. Mhm. So it's not simple rotation, as I said. It's an affine transformation which have combination of rotation, scaling, shear, stretch, everything. So we don't know exactly what is that exact transformation. We'll have to ourselves come out. But it can be, this transformation can be a combination of anything. It's not the simple translation, rotation, or scaling. It can be a multiplication, combination of multiple transformations. So how do we do this? So for that if we know it is just a simple rotation or simple transformation, we can directly apply that transformation matrix. But most of the time, but for this kind of she said, we will not know what is the relative position of each camera or things. So we don't know exactly the thing. But what we have is only these images. So from that images, can we estimate the transformation matrix? So that is the question. So we can do that. So to do that, we'll have to basically at least identify some pair of corresponding points, which are basically called control points or tie points. So for example, this is our original image and this is the destination image or the transformed image that we want. We would like to have at least 3 or 4 pair of points which basically map to the same location. So for example, in this case, we'll probably try to pick up these corners of the lake here and then the corners of the lake here, because we know these are the points which exactly correspond to the same location. So once we have to have a automatic method to find out those points, feature points. Later on in the course, we'll discuss those methods of feature selection and matching. But today we'll just do it manually. But let us say once we have this corresponding pair of points, then we can estimate our this transformation matrix using the simple mathematical equations and solving the mathematical equation. So how we'll do that? So as we said, our affine transformation matrix will have this kind of this kind of a representation where there will be 6 unknowns. These 6 unknowns we don't know. We want to estimate these 6 unknown in our transformation matrix. So to know these 6 unknowns, we'll at least need 3 pair of corresponding points, because 3 pairs of corresponding points will give us 6 equations. So because each point will have x and y. So using those three correspondence, so if you substitute the x and y values for those 3 pairs, we'll get 3 different equations, six equations, and for using those 6 equations, we can actually solve these 6 unknowns. And once we solve these 6 unknowns, we know our t. We'll get the t inverse, and with the t inverse, we'll be able to identify the actual coordinates from which the transformed coordinates have to come, and then we can do the gray level interpolation either using bilinear interpolation or nearest neighbor interpolation. So that's how we will generate our transformed image. So how we solve that? If you have 3 points, normally the 3 is the minimum points that you need. So we have 3 points in x in the original image, in the transformed image. We can represent this using this matrix equation. So let us say we represent this, this is x matrix and this is our u matrix. Then this is x is equal to u times t, and if you want to get t, we multiply by u inverse in each both side. So multiply by u inverse here and u inverse here. So so this will become identity, and now t will be equal to u inverse x. But normally what in practice, instead of using just 3 points, we'll try to get more points to get more accuracy, because any three random points may not really be the real representative set. So we'll try to have n number of correspondence points. But if we take more than 3 points, now this was square matrix, so we could take an inverse of this. But when this is not a square matrix, it has no you cannot invert it. So what we do, we go for a pseudo inverse. So this from your linear algebra. So in this case, our U matrix is no more a square matrix here. So what we do, we first multiply by transpose U transpose both side. So now this U transpose times U becomes a square matrix. So now this can be inverted easily. So now we take an inverse of U transpose U, multiply by the inverse on each side. So this will, here we'll just have T, and this will solve it. So this is basically called pseudo inverse method. So this is the way we get our estimate our transformation matrix. Of course, you don't have to actually implement it for you. Maybe in the exercise, I'll ask you, but most of the time in most of the platforms, for example, in MATLAB, we already have this function implemented. So I'm just going to show you some tools in the image processing toolbox which help you to do the image transformation. So I'm going to read those two images that I've shown you in the slide here. Then this is a tool which allows us to manually select the control points, type points. So CP select is the function in MATLAB which will help us to manually select the type points or the control points in the both the images. So these are the two images. I want to align one of them with respect to the other. So basically I can select the control points here which corresponds in this image and that image. So I'll try to use the corner points are good points for selection because they are more precise. So let us say I select one point here and the corresponding point here in the second image. Similarly, I can choose another corner point which is a good corner point. Let us say this one. So we need at least 3 points to do our to estimate our transformation matrix. Let me shift it. So let me select the third point here and the third point here. Maybe I'll select one more point somewhere here. Probably on this corner. So this tool basically helps us to choose the 4 corresponding points in both the images. So I'll go ahead and save these, export these points to the workspace. So the first pair of point from the one images are called moving points, and the other one will be stored in a variable called fixed point. I did not save it. Yeah, it has already been exported. Okay. So as you can see in the workspace, I've got these 2 points. So these are the xy locations of the other one. Similarly, this moving points is another set of xy locations. So now once we have these things, we can do a basically solve that system of equations. So there is an inbuilt function cp to t form which will help us to do that. So I am specifying this is an affine transformation. So based on that, it will solve and give us this T matrix. So this T form is some kind of a structure which has some, so it's a data structure here. So what is important here for us is in this so as you can see there is a T and T inverse. So this, so as you can see, T is a 3 by 3 matrix. 0 0 1 is the last one, and these are the 6 unknown parameters that has estimated. T inverse will be just the inverse of this matrix, so that if you want to go from the forward direction or in the backward direction, we'll have this. So basically now we can use this T inverse or T matrix to register, to do the registration. So now to transform this, there is a function I am transform. So I'm trying to align the first image I1 to the second image using the estimated transformation matrix, and while I do that I have to do a gray level interpolation. So I am specifying I will go for bilinear interpolation and we'll get the registered image as the output. So I can show you the, so as you can see the first image has been registered. You can actually see the other image also, probably it will have the I2 image. So this is a, so this is the registered image. It has been registered to the, so we can do an image difference here in order to see what is the difference, but you can see the, now this image has been more closely registered to the, aligned to the new image. It will not be a perfect one, it will have errors. If you have to more precisely you choose the control points, more precise you will be. This is another application of image registration. This is a demo of sometimes uh, when we are, when the camera, if the camera itself is on a moving platform, so that so normally when we do image object tracking and all that, if the camera is stationary, it's more easier to do it because the camera is fixed. We can simply do a subtraction, we'll be able to detect objects where they have moved and track them. But if the camera is on a moving platform like a drone or some kind of thing, then the tracking becomes more difficult. So in order to that, in order to do that, first of all we have to register these successive frames to the previous frames and then do the differencing and all. So this is just a demo where I basically I did some part here. So I'm just, so here this is a data set given by I think ARPA of US. So this is a drone video. They wanted to track these vehicles on the ground. So in the first image, there is basically what is being shown. The the feature points are being automatically detected. So normally these feature points are like edge points, uh, which will basically correspond. So using these feature points, they will estimate, the estimation is done so that the images can be, so we can see the transformed image is being getting shifted as and when the images are as well as when the camera is moving. So based on the difference of the image, I think the vehicles are being identified and then they are being tracked. So of course this is not the, so as you can see after sometimes you can only do this registration only to for once the camera is shifted a large, then you have to reset the entire frame. So there was some jerk art at this point, but just to show you that this kind of simple image registration can is a pre-processing or first important step before you do any complicated uh, computer vision application. Any question till this point? Hmm? Okay, so some other simple terminologies or concepts that I want to discuss here. So basically, I'm for your information, I'm just covering concepts which are given in chapter 2 of your Gonzalez book. Of course, they have not given in that detail the way I have covered, uh, but I've just taken. So in chapter 2, basically, we are just preparing you with basic operations and terminologies that may be used in the later chapters or later operations. So one of the things which may be useful later on is to understand how do we decide how do we basically decide whether one pixel is connected to the another pixel and which pixel is adjacent to another pixel, which is a neighbor of which pixel and so on. So that kind of a relationship, there is a formal definition we are just going to discuss here, because as we see later on we will like to segment out objects in this image and then basically determine, okay, this is object 1, this is object 2. We would like to give them labels, okay, this is an object 1, object 2, object 3 and so on, and then basically calculate the size and the area of each object in order to do further high level tasks. But to do that, first of all we have to decide whether pixels are if order to decide whether this forms one connected region, we need to decide that the pixels in this region or this object, they are connected. And how do we decide whether pixels are connected? So a broad definition of connectivity can be said that two points in image are connected if there is a digital path that can be found from, let us say, from P1 and P2 following pixels which satisfy certain criteria. Most commonly that criteria is that all those pixels should be of same intensity values, because if they are of same region they should have probably same intensity value. So normally we do it for binary images. Once we have segmented out images, made a binary images, probably this one region will correspond to one particular object or region, and then another region will correspond to another object. And then we need to decide, okay, this P1, all these pixels are connected to each other, so they form one object. All these pixels connected to each other, so they form another set or another object. Now, to do this, we have to know who is the neighbor of. So, in order to find a path between P1 and P2, we'll have to go through the neighbors of each pixel. So, how do we define neighbors? So, there are more than one ways we can define neighbors. We can define so for a given pixel px comma y here, we can say that it has four neighbors: the top, bottom, and the left and the right neighbors. So these are called basically four neighbors, or they are denoted by N4P. Another set of neighbors can be diagonal neighbors. So these are the four diagonal neighbors which are normally denoted by NDP. So for a given pixel P, these four pixels will form the diagonal neighbors. And many times we are interested in all the eight neighbors, including the four top and four neighbors and the diagonal neighbors. So these are denoted by N8P. So N8P is basically union of N4P and the diagonal neighbors. So depending on how you define your neighborhood, your result will differ. So that's why sometimes some algorithms use four neighbors, some algorithms use eight neighbors. So this is what we said earlier in a broad way. In a more precise way, say two pixels are connected if they are neighbors in some sense, either they are belong to the N4P set or N8 set, and their intensity values they satisfy certain criteria of similarity, either they are equal or within a certain range. In binary image, normally we have only two sets of values 0 and 1. So normally either we'll decide connectivity between 0 pixels or connectivity between 1 pixels. So our set V over which we define equality will be just either set 0 or set 1. In a gray level intensity value, we may have a larger set. So we may say that okay, all the pixel values having intensity range between 180 to 200, they will form one connected set if they are neighbor and if they all have intensity value within this set. This is just another term here. I'm just going to use. It's not so frequently used, but so as I said, four adjacency is basically if they are belonging to the set of if they are basically four neighbors. Eight adjacency is when they are basically two pixels p and q if they are basically eight neighbors of each other. But sometimes there is some other thing also called mixed adjacency. Mixed adjacency is defined slightly differently. So two pixels p and q with values from set V of equality are called M adjacent if either q is a neighbor of either four neighbor of p, so either uh, or if it is not one of the four neighbors, then it should be either the diagonal neighbor. Okay. So mixed adjacency is basically saying what it is saying is that either q belongs to the either q is one of the four neighbors of p, or if it should be one of the diagonal neighbors of P, provided both P and Q have no common four neighbors. P and Q have no common four neighbors. So what I'm just going to give an example, it will become more clear why. So sometimes mixed agency is basically useful because sometimes eight agency may cause ambiguity. So for example, here if you want to find out a path between a part within this pixel and this pixel. So if you want to go for eight connected path, so we can go from here to here, or we can go from if you are going for eight connectivity now this is also eight connected neighbor, this is also eight connected neighbor. So either we can take this path or we can go from this path and this to this path. So we have more than one possible eight connected path. So in this case, if we want to avoid this ambiguity, we can go for M connected path. So in that case, we'll only go for M adjacency. So now so for there is no four connect. If you only consider four adjacency, there is no path here between these two pixels will be disconnected because this is the only neighbor with value 1 and this is not one of the four neighbors of this, so it has no four connected path. Eight connected path, there are two different possible paths. If you want only single path, then you can go for a mixed adjacency. In mixed adjacency, what we defined, now these two are mixed. These two pixels are M adjacent because we said either they should be four neighbors or they should be diagonal neighbors, provided they don't have a common four neighbor. So now these two are diagonal neighbors and they don't have a common four neighbor. Their four neighbors are only this, and they don't belong to the set 1. So they don't have a common four neighbor. So these two are M adjacent. Similarly, when these two are four neighbors, so these are M adjacent. Now whether these two are M adjacent or not, so these two are not M adjacent because uh, although they are diagonal neighbors of them, but they have a common four neighbor, so there is no path between them. So basically M adjacency strikes out this possibility of path and it only leaves you a unique path. So sometimes if you want to have a unique connectivity path between two pixels, you can go for M adjacency. I'm just covering just for the sake of completion. Let me see how